So similar to our discussions about the common source amplifiers, we start common gate amplifier discussions and gain calculations with the assumption that lambda is 0. So there's no R0, but then over there we started with the same thing, and then we discussed what will happen if R0 is there. We're going to do the same thing here as well. So what will happen if lambda is greater than 0, or what will happen if we have R0 in the picture. So if I want to redraw the small signal model, this time with the R0 being present, I'm going to draw it this way. So I'm going to have gate and the gap between the gate and source. So let's call this VGS. Gate is connected to a DC, so it's going to be ground. Source is connected to VN. And I'm going to have this current source between source and drain. I'm going to call it GM VGS. And then there's this R0 here. And then there's RD to ground. Okay, so there's a difference, R0 and RD. There's a difference between R0 and RD. They're not in parallel because RD is to ground and R0 is to VN. Now, if I want to look at this and calculate the gain, I would say that, well, I know that for one thing, VN is from this node to ground, and VGS is from ground to this node, right? So I can still say VN is equal to negative VGS. Therefore, I can say GM VGS is really negative GM VN. So I'm going to write the KCL here. So I'm going to say Vout divided by RD plus Vout minus Vn divided by R0 plus GM VGS is equal to 0. Now, this plus GM VGS can be written as minus GM Vn because VGS is negative Vn. So I can say Vout times 1 over RD plus 1 over R0 is equal to GM plus 1 over R0 times Vn. So I took the terms that had Vn, this one and this one here, to the other side of the equation. Therefore, Vout over Vn is going to be 1 plus GM R0 over R0 over R0 plus RD over R0 RD. And then from here I can cancel R0s with each other and have this equal to RD times 1 plus GM R0 over R0 plus RD. Okay. Now, if we want to do a little bit of sanity check, we can say that if R0 goes to infinity, which means that lambda is actually equal to 0, then I can say that this expression is equal to RD times 1 plus GM R0 is going to be just GM R0. And R0 plus RD, I can just write it as R0 because, well, R0 is very much larger than RD. Then these two cancel and I get to GMRD that I had for the case with lambda is equal to 0. So this expression, at least with this check, seems to be correct. Okay. And about calculating the output resistance, let's look at this circuit. It's even more complicated. Now I have the source resistance included in the circuit. So again, the first thing I want to do is to look into the small signal model. So gate, and there's a VGS, and there's source is connected to some RS, to VN, gate is connected to ground, and then I have the current source, GM VGS, connected to R0, then from there to RD to ground. Okay, now if I want to know what is the resistance, the output resistance, because I've defined, so this is Vout. So the output resistance is the resistance looking into this Rout, right? I can tell that if I define this thing as Rout prime, I can say that easily that R out is equal to RD in parallel with R out prime, right? Because it's RD with whatever resistance they can see from this point forward, from this line, the green line to the right. Okay, and they're in parallel because they're both from the output node to ground. Okay, so all I need to do is to actually calculate the R out prime. So to do that, I know how to actually take care of this because I can actually, for output resistance, all I do is I connect this. So first I have to erase the stuff, this part of my circuit, and redraw it as Vx and Ix. Okay, so now when I connect the test source, I have to turn off any independent source, AC or DC. That's why I left this input floating, because I now have to connect it to ground. Okay, so the input is connected to ground. Now I have to find out what is the relationship between Vx and Ix. I'm going to use the same trick that I did when I was doing the same kind of, when I was answering the same kind of question for common source amplifier. Over there we said that this Ix is equal to I1 plus I2. And well, this I1 and I2 kind of add up at this node as well, so I can easily say this is also Ix if I write a KCL here and here, right? So Ix is equal to I1 plus I2, and well, here I'm saying the same thing. If this is I2 and this is I1, therefore their addition is going to be Ix. Okay, and since there's no current going this way, Ix is flowing, all of Ix is flowing through Rs. So based on this trick, I can say that the voltage at the source of my transistor, let's call it Vs, the voltage at the source is equal to Rs times Ix. Okay, therefore VGS, which is basically negative, this is Vg minus Vs, which is 0 minus Vs, is going to be negative Rs times Ix. Okay, now we have VGS. I can write the KCL at this node. So KCL at the output node tells me that Ix, which is the current that is coming in, is equal to I1, which is V out, or Vx actually, minus V source, which is we found it to be RSIX, divided by R naught, and I2, which is, well, GM VGS. So GM times VGS, which is negative RSIX. Great, I have everything based on Ix and Vx. So I just have to move things around and simplify the equation. So I know that Ix times 1 plus Rs divided by R naught plus GM times Rs is equal to Vx times 1 over R naught. Therefore, Ix times R naught plus Rs plus GM R naught Rs over R naught is equal to Vx divided by R naught. The two cancel, and I get Vx over Ix to be equal to GM R naught Rs plus R naught plus Rs. And you can imagine that the first term, GM R naught Rs, is much bigger than R naught and Rs because, well, it's their multiplication with each other. So knowing this and looking at this expression, we can see that it's exactly the same expression that we got for common source amplifiers with degeneration when lambda was greater than 0. And here we have the source degeneration, so it's not a surprising thing that this happened. Now R out, we said that it's going to be RD in parallel with R out prime. So this is R out prime. So my R out is going to be equal to RD in parallel with GM R naught RS plus R naught plus RS. So knowing that R naught is typically a large value and RS and RD are the same order of magnitude, you can imagine that the right side of this expression, so this term, is like extremely larger than RD, unless, well, we have a irregular RD. So I can say that for most of the time, I don't even need to plug in the numbers. I can imagine that this R out is most likely going to be just RD. Well, the only case that this is not going to be RD, or it's going to be approximately RD. The only case that it's not going to be RD is that, imagine if I replace this RD with a current source. Remember, we had we could actually use a PMOS transistor to implement a current source. So if I actually replace the RD with the current source, then the output impedance of that current source is also pretty large. So you have two really large terms in parallel with each other. In that case, you actually have to plug in the numbers and find out what's the numerical value. But those are just basically some notes or some intuition. In terms of solving circuits, you don't really need to remember those things. You just need to, what we did here was not really having any intuition when we started. We just basically drew the small signal model and wrote a couple of KCLs and simplified everything. We use the same method that we use all the time to calculate the output resistance. We apply a test voltage and find a relationship between the test voltage and the test current.